Assalamu alaikum. Today we will discuss about Laplace transform. Let's explore it. First of all, let's see the basic of this Laplace transform. At first, we will learn what is transform means. First of all, we have to understand the meaning of this transform. Under any other function operation like linear operator, differential, or any other operator operation, we find an output which comes from a certain input and they are in the same vector space. Now let's see what is the meaning of vector space. Suppose f of a is a function. F is a function of a variable, and after the operation we got an output which is also in the variable of a. Means here is also a function which is the variable of a, and here is another function but it's also a variable of a. Similarly, suppose f of v is another function, and after the operation of operator we find a function which is also in the variable v. So here from this function we got another function as output, but they are in the same variable. This is called the same vector space. Here suppose A is a vector space and V is also a vector space. Here we got output in the same vector space of our input. So here this is called same vector space, and this in the same vector space these operations are called the operator. Let's see an example of this operator. Suppose here is a linear operator differential of e to the power minus x square. If we differentiate this function, we will got minus 2x e to the power minus x square. Let's see that it is, suppose it is a function of f of x, and we got of another function, suppose it is of g of x. They are different function, but notice that it is also a function of x variable and it's also a function of x variable, means they lies in the same vector space. But if our input function is variable of v variable and we got an output of a function which is include a variable of w, means there is a function which is in v variable and we got different variables in our output as different function. This is called the different vector space. So what is different vector space? They are transformed from one variable functions to another variable functions. This is the different vector space, and this conversion is called transform. If we got our output from same vector space to another function of same vector space, then that is not called transform, that is operator. And if we got a function from another variable function, then this is called the transform. Let's see an example of this different vector space. Suppose it's the integration of x square into y square dx. Then we will got output as y cube by 3. Here this is a function of f of x and y, means here the variables are x and y, and we got the output as a function of f of y. So we transform this function into different vector space. This is called the transform. Now let's see the Laplace transform. What is Laplace transform? It is a method that used to convert, the main operation of this Laplace transform is to convert a function from it converts from time domain signal into frequency domain signal. Suppose f of t is a time domain signal and f of s is a frequency domain signal. So what this Laplace transform does? This converts the time domain signal into a frequency domain signal. This transform also helps to solve differential equations, complex differential equations, by turning them into algebraic equations which we can solve easily. So it helps to solve our equations by make it easier. Now let's see why are we learning this. We all have the same questions that why we are learning this. Means we are finding the real life use of our learning. Let's see the real life use of this Laplace transform. Imagine a complex circuit or any mechanical system. Instead of working with this, it behaves over time, which involves calculus. The Laplace transform changes it into simpler frequency domain equations, which we can solve easily using algebra. Means in the complex circuit or mechanical system, there are used some time domain signal, which is the complex calculus, which seems difficult to solve. But this Laplace transform changes that complex equations into a frequency based equations, which is simpler than earlier, and we can solve this easily with algebra. Once solved, you can use the inverse Laplace transform to get back the time-based result. Suppose we have to get back into our first time-based result, or we need to find the time-based result. Then we will use the inverse Laplace transform and we will get our time-based result easily. For starting the formula of Laplace transform, let's see the integral transform, basic integral transform. Suppose f of t, a basic function of time domain signal. Let's transform this time domain signal. After transforming this time domain signal, we will find a frequency domain signal, and if we break this frequency domain signal, we will find integral from a to b, f of t main function and a function of kernel function, which is a function of variable s and t. This is called kernel function. In Fourier transform, this kernel function is equals to e to the power minus ist, and in our Laplace transform, this kernel function is e to the power minus st, where the s is a complex frequency signal and t is the time domain signal. Now let's see the basic formula of our Laplace transform. The basic formula of Laplace transform is this. This is the sign of Laplace transform. You can easily write it as L, and it is our required given function, which is in the time domain signal, and will transform it into a complex frequency domain signal. If we break this in Laplace transform, it will be integral of 0 to infinity e to the power minus st, which is the kernel function for the Laplace transform, and f of t dt. This is our given time domain signal. This is the main formula of our Laplace transform. By using this formula, we can solve many complex time domain signal into simpler frequency domain signal. Now let's see another important topic, existence of this Laplace transform. This Laplace transform does not exist for every given function. Let's see the conditions for this Laplace transform. For this Laplace transform of a function, suppose f of t to exist, means f of t will exist to transform into the Laplace transform if it satisfies some conditions. Certain conditions must be satisfied. These conditions ensure that the integral. Let's see the conditions of a function being to be exist for the Laplace transform. This is the basic formula of our Laplace transform, which converges to a finite value. This function converges to a finite value. Let's see the conditions for the existence. The given function f of t, this function is to be piecewise continuous. A most important thing is this function must be piecewise continuous. Means the f of t can be broken into sections. Means this f of t can be broken into sections where it is continuous, and in those sections this function must be continuous. It have finite jumps but no finite discontinuous. Means it will have no finite discontinuous, and it can jump from one to another value. Example of this piecewise continuous is step functions, sinusoids, exponential functions, etc. Let's see an example of this piecewise function to understand it clearly. Suppose this is an example of unit delay function. This unit delay function is defined as like this. When suppose this is a function and it is defined into two portions. If this t is greater than a, then it will give a value 1, and if it is less than a, then it will give a value 0, means it will give us nothing. Let's draw its graph. this look like kind of this. Suppose this is 1 in value and this is a. So this for here said that if t is greater than a, means if is t is greater than a, so there this function will give the value 1. So according to this function will be valid 1 from this point to infinity. And as here the value of t is less than a, then this function will give the output as 0. So here the output of this function will be 0. Here we saw that this is a piecewise function and it gives us value from this point, and here it gives us nothing. So for this particular value we will give a continuous function. This is called piecewise continuous function. Suppose this is another example and this function exists here, 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 like this. Means it is piecewise behind among these, etc. And it is continuous here as a certain value. Suppose a, here continuous a certain value with a certain value of b. Here also a, means it is piecewise but it is continuous in those certain values. So this is called piecewise continuous. Let's see the second and another condition of this Laplace transform. So the given function f of t is of exponential order. So our given function must be of the exponential order. Now what is exponential order? This is our given function. So the value of our given function must be lower than the exponential value. Suppose m is a constant and this is a function of exponential order. So our function f of t must be lower or equal than these equations. Let's see the graph to understand more clearly. Suppose the graph of this exponential function is like this. This is a function of exponential order, and the required this f of t function is like this. Means it is lower to the, this exponential is go upwards to the infinity, and the our function that given it is like this. So this function is lower than this exponential order function in the graph. So this function is exist for our Laplace transform. We can also do the sinusoidal function. This is our exponential function and our sinusoidal function is like this. Means it will go upwards and it will go here to the infinity, but it will not cross this line. So this is also exist for our Laplace transform. But if this our exponential order function and our f of t means required function is like this, means it crosses the exponential function, then this will not exist for our Laplace transform. So I hope you understand these two conditions for the existence of a function being exist for the Laplace transform.